Hi, this is Roger from Kanka Labs, and this is the second part of our comparison of four different component or semiconductor analyzers. Just two additions from part one. I've checked the firmware versions of the two Peak Atlas testers. Both were one version behind the momentary latest one, and as you know, this one is not upgradable, so it has, I think, version 2.97, and the homepage of Peak Atlas says that the latest version is 3.0x. And this one here was software upgradable, and I've upgraded to the latest firmware. You can find the details in the downloadable Excel sheet where all the data are continuously updated. New versions I found, and special issues with the testers. And another addition which I didn't mention, how you can differentiate between Schottky diodes and germanium diodes, and we'll take a look at first at a test with the fish of a Schottky diode. As you know, or as you probably might know, Schottky and germanium diodes have both relatively low and undistinguishable forward voltages in the range, depending on the forward current, around 300 millivolts. But their reverse current is very different. Although Schottky diodes do have a greater reverse current than silicon diodes. So with a Schottky diode we get around 60 nanoamps reverse current. And now let's change to a germanium diode. It's a AA143 in this case, and we will see that the reverse current is now in the microamps region. You even could experiment with heating it up, and you will see that the reverse current of germanium diodes and also transistors increases significantly with temperature. Perhaps we can even simulate this here when I've heated it with my fingers. Yeah, you see now it's 2 microamps. So that's a way, if you absolutely have no markings on your diode and don't know if it's a germanium or a Schottky diode, you cannot find out from the forward voltage. They are nearly equal, but the reverse current of germanium diodes is always in the microamps region, while Schottky diodes are in the region of a few dozen nanoamps typically. So let's start our comparison with transistors with an old germanium transistor. It's an AC187, and let's see, I only have one of them available, so we can't test them in parallel. What does the AS4002 show us? We get the typically low base emitter voltage of germanium transistors of, let's wait again, of 0.13 volts at a base current of 8.8 microamps. That's the reason why germanium transistors still have some application, because of their very low base emitter turn-on voltage. So what else do we see? A current amplification around 360. We get a reverse current of 477 microamps, so that's also quite typical of germanium transistors. They have, as we already saw with the germanium diode, they have very high reverse currents. And last info we got was the amplification factor, HFE, was measured at a, let's wait again, at an emitter current or collector current of 3.55 milliamps. So quite a lot of information for this little tester. Now let's see what the fish is telling us. And I expect much less information. And yeah, first of all, it doesn't correctly identify it as a germanium transistor. It only says a bipolar junction. Of course, this is correct, but you have to deduct again that it's a germanium transistor from the low forward voltage, which is the base emitter voltage here. It only measures a current amplification factor of 15. So that's totally different from what the AS4002 tells us. And again, we don't know at which... now we get a different value. It might have been a contact problem. Now we get something that is more correct. An HFE of 294, which is more like what the AS4002 told us. So that might be a little glitch have been what we have seen here. Forward voltage of slightly above 100 millivolts. And let's see if the third time it tells us again halfway correct values. Yeah. Okay, so apparently the first measurement was a glitch. Anyway, we don't get very much information. The correct pinout, that it's a bipolar junction transistor, but we only get the base emitter voltage and the current amplification factor. Again, we don't know what is the base current and what is the collector current, but anyway, for identifying and this transistor, it's okay, but it could be better. So let's change to the DCA 55 from Peak Atlas. Again, it takes some time to fasten the test clips and start the measurement. And we get correctly an NPN germanium transistor, a current gain that is nearly equal in all three testers, measured at a test current of collector current of 2.5 milliamps, the typically low base emitter voltage of 0.21 volts, measured at a base current of, this time it's the base current of 5.24 milliamps, and a leakage current also, again, as we already saw with the AS4002, quite high. In this case, 1.29 milliamps. Okay, that was all. I think sufficiently enough information. Good result that it perfectly identified it as a germanium transistor. And now let's take a look at what the more expensive DCA 75 will tell us after its test cycle. Perhaps you might notice that the contrast is a little bit better than at the first video. I noticed when you connect it via USB to the dedicated program, you can set the contrast of the LCD only with the Windows program, not here as a standalone device. So what do we get? An NPN germanium with a current gain of 350, well within the range of the other two ones which gave good results. Remember, the current gain is not a constant for a bipolar junction transistor. It depends on the collector current with which you measure it, so that must not be a measurement error, but let's see at which here. Now it has measured it at 5 milliamps collector current and a base emitter voltage of 2.209 volts measured at a relatively high base current of 5 milliamps again, and a saturation voltage in the collector emitter of 13 millivolts, so very low saturation voltage, also typically of germanium transistors. measured at 5 milliamps collector current and 1 milliamps base current. So, and the leakage current again in the range of 1.1 microamps or 1094 milliamps. It's a little bit exaggerated to display 4 decimal places here. A little bit of rounding would be better for giving a good readable result. So a lot of information. Now the cyclic oh man, the scrolling has turned back to the start, and I would say the 3 here give the best results: correct identification of a germanium transistor, and the Peak Atlas gave us the most data. Second place would be these on par, and this time the fish, I'm not very content with the result. So now let's go over to classical silicon bipolar junction transistors. So this time I've chosen a PNP just to make it, not to make it too boring, a BC557B. The AS4002 correctly says it's a silicon bipolar junction PNP. It measures a current gain of 251, a base emitter voltage typically of silicon transistors of 0.68 volts. The current gain is measured at 2.8 milliamps, collector current. And what else do we get? The reverse current is non-measurable, which means below 100 nanoamps. That's the limit the AS4002 can measure the reverse current. And finally, the base current at which the measurement was made, it's 11 microamps. So again, sufficient information to identify and to sort the transistor. Let's see what the fish is doing. What I always find good is that they make good use of the graphical LCD, which clearly shows the symbol of the PNP transistor, but we only get 2 data: the current amplification, nearly exactly the same as with the AS4002, 250, and the base emitter voltage. Perhaps they shouldn't say forward voltage. VBE would be perhaps better to understand that it's the base emitter voltage, but again we don't get the measured collector current where this value is gotten from, and nevertheless quite okay. Let's see what the small atlas is telling us. PNP, current gain of 308 at a collector current of 2.5 milliamps. That's obviously the standard collector current. Base emitter voltage of 0.78. If you wonder why it's always higher than with the other 2, that's because they measure the base emitter voltage, the Peak Atlas ones. They are measuring it at relatively high base currents at 4.62 milliamps. So where the transistor is fully switched on. And the leakage current, again, it's not measurable, below 10 microamps. That's the limiting range. And okay, enough information. And I expect now again from the more expensive DCA75 to give us some more information. Again, the correct symbol, correctly PNP silicon transistor, a current gain of 271. So this one was perhaps a little bit out of range with the current gain. Measured collector current 5 milliamps, base emitter voltage 0.818 volt, measured at also 5 milliamps base current. A saturation voltage, that's quite a nice feature, that it gives us the saturation voltage at a collector current of 5 milliamps and a base current of 1 milliamps. and the leakage current, this here can measure apparently down to 1 microamps, and it's below 1 microamps, which tells us the transistor is okay and not damaged, and that was it. Okay, quite good results from all four. Again, the least information from the fish, but sufficient for identifying. The others give a bit more information, and top is the DCA-75. So let's go over to a Darlington transistor. So I've chosen a PNP Darlington, a BC516, and Darlingtons come in some are coming in some variations. They can have an internal resistor from base to emitter, and they also can have a reverse protection diode from collector to emitter. Both are shown with different symbols when the AS4002 detects this. This simple Darlington does not have any base emitter resistor or reverse protection diode. What we see is it's represented as DT, which is the short form here in the limited alphanumeric display of Darlington transistor. We get the pinout, and let's see, the current gain cannot be measured here. There you get 3 minus signs. That's because the limit of the current gain the AS4002 can measure is 999, and Darlingtons usually have current gains of more than 1000. But anyway, what else do we get? The base emitter voltage of 1.32 volts. That's exactly what 2 base emitter voltages of a silicon transistor give when they are cascaded. As you will know, a Darlington is nothing else but 2 cascaded transistors. And we get a reverse current of 0, which means it's below 100 nanoamps. And what else do we get? The base current is 0.9 microamps. So except for the non-measurable or non-displayable current gain, quite okay. You might have asked yourself, how does it know that it's a Darlington transistor? It's not through the high current gain, but it's because the base emitter voltage is exactly 2 silicon diodes. The algorithm is simply when the base emitter voltage is greater than, let's say, 1 volts, it must be a Darlington transistor, or it's the device assumes it's a Darlington transistor. Now let's go over to the fish and see what it is displaying. Yeah, it tells us it's a PNP, but it does not show the correct symbol for a Darlington transistor. So again, a little bit on the downside. Here the current gain is displayed as 30.8K, which is 30,800, so quite high, and the forward voltage is 1.24 volts. So you must deduct from yourself from the high current gain and especially from the high base emitter voltage that it must be a Darlington. But it could identify this as directly as a Darlington and show the correct symbol. Let's see if the Peak Atlas DCA-55 is doing any better. It clearly displays us PNP Darlington. Current gain is even higher than what the fish has measured, nearly 60,000. Measured at a test current of 2.5 milliamps. The base emitter voltage is 1.41 volts, again measured at a high base current of, in this case, nearly 4 milliamps. And the leakage current again is 0 or below 10 microamps. So quite okay for the DCA-55. And now let's go to the DCA Pro, the DCA-75. Now here we have the correct symbol of a PNP Darlington. Apparently the current gain is higher than the limit. It only tells us greater than 32,000, but anyway relatively okay. Let's see what else do we get. Collector current was 5 milliamps. The base emitter voltage 1.442 volts at a base current of 5 milliamps. And again the nice feature giving us the saturation voltage of 0.653 volts measured at a collector current of 5 milliamps and a base current of 1 milliamps, as we already have seen. So best result I would say is the DCA75 followed by its smaller brother, and then the AS4002 and the fish on the two last places. Okay, let's that will be it for standard silicon or germanium transistors, bipolar junction transistors. Now let's take a look at what the four are doing with JFETs. So I've put in a BF245C N-channel JFET, and let's see what the AS4002 is displaying correctly. N-channel JFET. Now many JFETs or junction FETs do have a symmetrical buildup, which means drain and source are interchangeable and that way cannot be distinguished. We'll see later if we'll compare it if the source and drain pinout here is given the right way, or if it doesn't matter with this transistor. So anyway, what else do we get? We get the RDS on of 125 ohms. That's the resistance of the drain source or drain to source when the JFET is fully turned on. We get the threshold voltage of minus 4 point something volt. The threshold voltage of a JFET is that voltage, that negative voltage, when it starts to conduct. And we get finally the drain source current when it's fully turned on of 16.4 milliamps. Fully turned on means for a JFET when the gate voltage is 0 volt. Remember, the JFET is turned off with a negative gate voltage and then starts to conduct when the negative voltage comes nearer to 0 volt. It is fully conducting at 0 volts gate voltage, and you shouldn't get any higher. You shouldn't get into the positive gate voltages, because then the parasitic diode starts to conduct. So that's at least what's true for an N-channel JFET. Let's see what the FISH 8840 is giving us. Okay, we get the pinout, and pin 1 is the gate. That's the same as here. Pin 2 is set to be the drain, and here we have pin 2 as the source. So apparently here we can see the effect of the symmetrical JFETs. Here they give different pinouts for drain and source, but that's not an error. It can't be distinguished which one is the drain and which one is the source, because they behave exactly the same. So what else do we get? A gate source voltage of 2.6 volt. I think more correct would be minus 2.6 volt. And at this gate source voltage we get 3.7 milliamps. So the information of the fish could be better. At least we get a halfway correct pinout, the right symbol. Halfway correct, I mean it could also be the other way around concerning source and drain. And we get one pair of parameters, the drain current measured at one specific gate source voltage. So let's see what the DCA55 gives us. N-channel junction FET is correct. Drain and source not identified, that's what I told you. The peak atlas recognizes that drain and source are symmetrical and that they cannot be correctly identified. So in the pinout, it only tells us at which colored lead the gate is. And that was all. So that's a little bit on the downside. I could give a little bit more information. That's a little bit disappointing. Let's see what its bigger brother is telling us. Okay, N-channel JFET, symmetrical source and drain, so the correct symbol, but it won't tell us. Only the blue test lead is the gate. The source and drain are interchangeable. We get a turn-off voltage that was the same as here, the threshold voltage of minus 5.22 volts. Again, we have to know, well, what is the turn-off or threshold current that this is related to? And this is related to 4.8 microamps, where the gate source voltage of minus 4.22 volts belongs to. Next is the turn on voltage measured, now that was a little bit too fast, at minus 2.72 volts at a drain current of 5 milliamps. So that's around what we got here. A gate source voltage of, it should be correctly, minus 2.6 volt and at a drain current of 3.7 milliamps. So you also can see when you compare the values that there is a great there are great differences. You cannot absolutely trust these values. They are only a hint about what the real curves of the transistor look like. So let's see again, what else do we get as information? We get the amplification factor of 3 milliamps per volt. Remember, a JFET is a voltage controlled current source, so we in difference to bipolar junction transistors, which are current controlled current sources where we get a current gain, here we have a drain current controlled by the gate voltage, and thereby the amplification factor is, concerning the units, is in milliamps per volt. And that was measured at a drain current of 3 milliamps, or between 3 and 5 milliamps, because you have to measure at least 2 points to get the gain factor. And the drain source saturation current is greater than 12 milliamps, measured at a drain source voltage of 2.12 volts. So quite a lot of information. The RDS on, the on resistance of the drain source is 102.9 ohms, relatively near to the 127 ohms we got from the AS4002. Measured at a drain current of 5 milliamps and a gate source voltage of 0 volts, which means fully turned on. So that was quite a lot of information here from the DCA75. So I would say this is the best. This is second, and these two come at the ranks 3 and 4. So let's continue with MOSFETs. Well, what you should know if you don't, there are 4 types of MOSFETs. First of all, we have N-channel and P-channel MOSFETs. That's like with JFETs. but they are further divided into enhancement and depletion MOSFETs. Well, depletion MOSFETs are rarely used, and only one of the testers is able to identify depletion MOSFETs, and that's the DCA-75. The other ones can't test depletion MOSFETs, but the most used ones are so-called enhancement MOSFETs. These are the usual types you use in switch mode power supplies or for any kind of switching. And just to check if they recognize that, of course, P-channel MOSFETs have negative voltages at their gate. I have put at least 3 P-channel MOSFETs. I didn't have more at hand into the testers. Well, and the AS4002 correctly gives us a P MOSFET, P-channel MOSFET. It must be an enhancement type because it cannot test depletion MOSFETs. We get the pinout, drain, gate and source, and 2 measurement values. The threshold voltage where the MOSFET starts to conduct, that is at minus 2.41 volts, related to a drain current of 2.27 milliamps. So enough of information to identify the kind of MOSFET. Let's see what we get from the FISH 8840. The battery is already starting to get weak due to the extensive testing. And well, we get the pinout, we get P-channel enhancement MOSFET, a little bit abbreviated but sufficient to recognize the part. We get the connection diagram and the symbol of a P-channel MOSFET. Obviously, it also has detected the reverse body diode. Again, too fast, auto power off. And let's see what other values we get. Well, we get not only the pinout with source, gate and drain, but also the gate capacitance. It only says C here, but from the datasheet you can read that it's the gate capacitance, which is the most important of the 3 capacitances you have between the 3 terminals. And we get a threshold voltage of, here it's without the minus sign, so again you can deduct this because it's a P-channel type that it must be a negative threshold voltage. Anyway, 3.2 volts, but again the drain current this is related to is not given. It is always with a FISH in the range of 6 milliamps, but it varies a little bit depending on the type of device under test you are using. So it doesn't measure directly the drain or collector current if it's bipolar junction transistors. Anyway, enough to identify the part. And nice feature is that we get the gate capacitance, which none of the others will give us. Let's see what the DCA-55 tells us. Again, P-channel MOSFET, correct. We have to scroll for the colors of the test leads to identify gate, drain and source. We get the threshold voltage of and the related test current, the related drain current. So that was it, nearly identical in information to the AS4002, and let's expect a little bit more from the more expensive DCA-75. Well, we get a nice symbol of the component of a P-channel MOSFET, again with the body diode or a reverse protection diode. We get the which component it is in clear text, NChannel enhancement mode MOSFET, the colors of the test leads, and let's see when we scroll down we get the turn on voltage of 2.446 volt. Again, 1 digit less would have been better. We get the related drain current. In this case it's always with the DCA-75 around 5 milliamps. we get a gate current of 1 microamp. Now don't overinterpret this. It could also be 0 because usually a MOSFET has only nanoamps or picoamps of gate leakage current. So it mustn't be 1 microamp. It could also be much lower. We get the turn off voltage. That's something new when the current, the drain current, falls to near 0. And here this is determined at a drain current of 4.9 microamps. And we get the transconductance, which is the kind of gain a FET does have, with 30.3 milliamps per volt, measured at a drain current between 3 and 5 milliamps. To determine the transconductance, you have to measure at least 2 points of the drain current and the related gate voltages. So that's why here it is measured at ID 3 milliamps to 5 milliamps. You need at least 2 points, or better 3 points, to get a correct transconductance. And we also get, nice feature, the RDS on, the drain source on resistance when it's fully turned on, with a value of 1.1 ohms. So quite a lot of information measured. The RDS on was measured at 5 milliamps. By the way, here, if you didn't recognize it already, because I only had 3 P-channel MOSFETs, I had to use the companion type N-channel. So this was not a wrong result when it told us N-channel MOSFET. It's just because I didn't have 4 identical P-channel types. So, and finally we get related still to the RDS on, not only the drain current but also the related gate source voltage of 8 volts, which is, because this one here can go up to 12 volts test voltage, which is quite nice, because some power MOSFETs, they don't turn on at 5 volts, which all the other 3 types are measuring, or they don't fully turn on. And we get the body diode in clear text. So the best result, I would say, is here from the expensive DCA 75, and all the others are nearly equal in getting the result. All correctly identify if it's N or P channel MOSFET, and at least one pair of measured values, usually the threshold voltage and the corresponding drain current. So let's go over to the next kind of transistor, and that will be a very special one you perhaps never have heard of before. So next we are testing is a so-called IGBT, that is an insulated gate bipolar transistor. It is a kind of mix between a MOSFET and a bipolar transistor. You can imagine it as being controlled with a gate like a MOSFET, but there is no drain source. There is, just as in a bipolar transistor, there is collector and emitter. And as you, it's nearly only the Atlas DCA 75 is able to recognize. So to quicken up the test, I will not try all of them. The fish only gives us, it can only measure a capacitor, which is of course totally wrong. It's obviously the gate capacitance that it measures here, just as with a MOSFET. Let's see what the DCA 75 is giving us as a result, because from the data sheet it claims to be able to identify IGBTs. By the way, if you, they are rarely used in hobby electronics. I encountered them only once when building my Tesla coil, where a P and an N channel pair are used, but they are usually only used in high power electronics like locomotives and something like that. So it's no wonder if you never have heard of them before. Here you can see from the component symbol that they are really a mix. You have a gate which looks like at a MOSFET, and you have a collector emitter, just as with a bipolar transistor. So what we already saw, the DCA75 could identify it in N-channel enhancement mode IGBT. Let's see if we get some values. Yeah, it even measures some values. Here we have a VGE on, that is the voltage where from gate to emitter, not from gate to source, where it turns on. That is 5.091 volts. Perhaps another reason why the others couldn't identify them, because to turn on it needs substantially high voltage, because it's a power transistor, a power IGBT. It needs nearly 5 volts or a bit over 5 volts to give a collector current of 5 milliamps. And that was it, the information. Well, anyway, there's missed something. We get the gate current. This time it's 0 microamps, so below the measurement limit of the tester. We get a turn off voltage, again from gate to emitter, of 4.06 volts, measured at a collector current of 5 microamps. So it looks, the values are similar to a MOSFET, but remember, we don't have a drain source, we have a collector emitter here. And we even get the transconductance, so nearly all the values that we also got from a MOSFET at a collector current from 3 to 5 milliamps. We get the saturation voltage from collector to emitter. So now we get the values that we also got from bipolar transistors at 5 milliamps collector current and at gate emitter voltage of 8 volts. So again, quite a substantial mass of information we get, and we, as you could see, all the others are not able neither to identify nor to measure any data from that. So quite good. And now finally, again, and the last transistor type we test, again a type you might never have heard of before, and that's a so-called uni-junction transistor. So uni-junction transistors were a bit hip in the 1970s. They have 2 bases. As you can see here, we have base number 1, base number 2, and only 1 emitter. We even get some values. RBB seems to be the resistance between the 2 bases. So it's a very special kind of transistor, rarely used in today's circuits. And it's a nice feature. You will see the AS4002 is the only one to identify uni-junction transistors. What they were used for, or the only circuit I can remember where they were used, is you can build a kind of rectangle, a square wave oscillator with them, with only 1 transistor and I don't know, 1 or 2 other passive components. But as I said, rarely used today, so it's nice that the AS4002 can identify them and even give some data, but the others will probably only measure a diode or something like that. Let's see. And yeah, we get the 2 base emitter diodes, so you cannot deduct anything more from that. But I don't think that this is something very important, because you nearly never encounter a uni-junction transistor. You even can see from the case which is also rarely used today, these small metal cans, that it's a somewhat outdated type of transistor. Let's see what the peak DCA-75, no, it says no component detected. So, no worry, that was just a little addendum, because I knew that the AS4002 was able to measure uni-junction transistors. So that were all the kind of transistors I could find that the testers can either identify or give us some data. And now we still have one other type of components with 3 pins or standard semiconductors, and that are in Europe we call them Thyristors. In other places of the world they are more known as SCRs, silicon controlled rectifiers, and their cousins the TRIACs. So there is one thing in common with thyristors or SCRs and TRIACs. What you might know, they need a certain gate current to turn on, like a switch. And depending on the height of the minimum gate current, that is the determining factor if the analyzers can recognize them. So because they only can deliver something between 5 and 10 milliamps, depending on the type of gate current, only so-called a low gate current or low power SCRs or TRIACs can be tested. I will show you in a minute a type which they don't recognize, but let's start with a standard thyristor or SCR. It's a TIC106D, and the AS4002 tells us correctly it's an SCR, and the pinout, the cathode, anode, and the gate. Now let's see with the same type what we get from the FISH 8840. And we get cathode, anode, and gate, also only the pinout, and that's common to all of our testers. We get no further data. Here we get sensitive or low power thyristor. So you see they all mix up. Some call them thyristors, some SCRs. You should know that both is the same. We get the pinout, gate, cathode, and anode, and that was it. And except for the component symbol, what I just recognized, we don't get the component symbol as far as I remember. Let's try the test again. No, we only get the pinout, so that's a little bit disappointing. The great thing about the graphic display is the ability to show the component symbol as we get correctly here, and no further data. But so all of them give us basically the same result. If now with or without a symbol, it's perhaps not so important. Now let's change to a TRIAC as the next and final part in this episode to test. So with TRIACs we will see we still have a bigger problem with the necessary gate current to turn them on. I've selected the lowest gate current types that I could easily get hold of, and the AS4002, even though gives us a wrong result, it only tells us this TRIAC, it's a BT136/600. It only tells us it's an SCR. That might be due to the fact the gate current in the to turn the TRIAC on in the one direction is usually different from the gate current you need in the other direction. So due to the data sheet, it should be able to identify TRIACs, and so I'm not 100% sure if this wrong result here is not due to the fact that this type, and I've tested a few others, they give the same result. It only tells us SCR, but it might be due to the fact that the negative gate current to turn the TRIAC on is just, it cannot reach that high. Now let's see what the fish is doing with a another type, also with a moderately low gate current. Well, and this type here, it's a TIC225D. It wrongly identifies it as an NPN transistor, so that might be also due to not being able to deliver enough gate current. Let's try the other type, which needs a little bit less gate current to turn on. And yeah, now it's correctly saying TRIAC, again without the component symbol, perhaps due to that the flash is simply full and there is no more space to store the graphic symbols of a Thyristor and a TRIAC. Anyway, we get the correct pinout, but only if it is able to turn on both positive and negative gate currents. So let's see with the low power type. I call it low power, or better to say low gate current. If the DCA 55 from Peak Atlas is identifying it, and yes, sensitive or low power TRIAC, the two main terminals and the gate are identified and no more other information. Now let's try the same with the type that it needs slightly higher gate currents, the TIC226M. Again, it's a really annoying to fiddle around with the little clips instead of putting them in a socket. And now unknown faulty components. So the slightly lower power type was needed just enough gate current for this model to turn it on. And now in the more expensive one, I've put in also the medium current type, and it should be able, yeah, it correctly identifies correct component symbol, no more further information, no measurement data. And but also here we are at the limit of deliverable gate current. I can show this with the next higher type, the TIC226M, and you will see, because I've tested it before, that it cannot turn the TRIAC on. You see, no component detected. So all of them are not very suitable to test TRIACs or Thyristors, SCRs. There are specialized Thyristor and TRIAC-tester. Peak Atlas does have one of these special testers. It's just pure luck if you can't read anymore the writing on your component and cannot look up the data sheet. You might think, well, this could also be a power transistor, it could be a power voltage regulator, and it's nearly pure luck if one of them can identify them. So we should not overestimate the more or less positive or negative results we get from them. It's a nice feature if it correctly identifies this one. And I also show you another strange result with this TIC226M, which needs the most gate current of all TRIACs we had. And at least when I tried it out before, I got a resistor as now. So that is, of course, totally wrong. Again, here it would be better if the fish told us unidentifiable component. Anyway, thyristors and TRIACs are not the strength of all the four testers. The best, again, is the most expensive one, and but don't overestimate Thyristor and TRIAC testing. So that was it for today, and in the next and probably final part we will look at some specialties of the testers, which special components each one of them has, except for the DCA55, it's really we have everything that this one could test was already tested, but the other three ones, they all have now some special features. Here we will see that it can test optocouplers. A very interesting feature with the FISH 8840 is testing it serves nearly as an LCR-Meter. It can test inductances, inductors, capacitors and resistors, even 3-pin resistors like potentiometers or resistor trimmers. And the DCA75 can measure voltage regulators, the standard 3-pin types like the 7805, and it has a unique feature. It can be connected to a PC and do some curve testing, but probably this will be a special episode, because I also have two other transistor curve tracers, and we should do the curve tracing ability in a separate video, and I will take all four of them apart to show you what's inside, make a little analysis of the, at least this, on the surface, a little bit analysis of the circuit. And one thing before I forget it, we deliver the FISH 8840 with 3 different colored test lens with these mini grabbers, just as a result from the experience here from the test, that I think it's quite nice to have 3 test leads with mini grabbers. And there is another feature. This one has a self-test and self-adjustment, and how this works I will also show you in the next and perhaps or probably final episode. So thanks for watching this long comparison. Anyway, I hope you liked it. If yes, then give it a big thumbs up. Or leave your comments about questions, and perhaps you know other component analyzers that I don't know of, which we also could compare to these 4 ones. So until next time, bye from Roger, bye from Kanka Labs.